All right, so picking up where I left off there a minute ago. Actually, it was it was a lot longer ago than that. What ended up happening is I don't know, something happened with the file. So let's get going here. Let's talk about random variables of the continuous type. Okay. All right. So random variables of the continuous type come equipped with a distribution function also. We call this the density for the random variable. Okay, and we notate that by little f at x. And little f at x has the property that, remember I said you want to concentrate on continuous random variables having the property that you want to pay attention to where they fall in an interval of values. The probability of being equal to any particular value is effectively 0 now. So the probability that x falls between two given numbers, a and b, is just the integral of that density function. Okay, we'll call that the density. We'll just say the density. So before, in the discrete case, we had the so-called probability mass function. And that was, that thing told you the probability of being equal to any particular value. But now that's 0. Now we're only interested in the probability of being in an interval of values. And that's gotten at by taking the density and integrating the density over that interval. Okay, so now we're, instead of dealing with sums of things, we're dealing with integrals of things. Okay, so and the key here is that whether we're talking about x being on the closed interval from a to b, that's what that first thing is, like x could be equal to a or equal to b, or it could be on the half open interval, closed at a, open at b, or open at a and closed at b. That means that I'm in the first case I'm allowed to be equal to a but not to b. I'm not allowed to be equal to a, but am allowed to be equal to b. Or you can just be on the open interval from a to b. So I eliminate equality at both ends. Any of those is going to have the same probability now, because being equal to anything is 0. Probability 0. So basically the probability is the integral of that thing, and that means that it's the area under the graph of that density function from a to b. Okay? And here's a little picture of what that looks like. So that's the probability that x is between a and b is just given by the area under the density function between a and b. Okay. So densities have to have a couple of properties, of course. Like if I were to integrate over all possible x values, the density function, that's what that first box thing is, I should get 1. Okay, clearly. If I integrate over all possible x values, I should get 100%. Since little f is supposed to be telling me probabilities of being, in various intervals. Okay. Secondly, of course, the density function can't ever be like negative. Okay. So, I mean, these properties are kind of like what we had before in the discrete case, where we said the sum of the probability mass function over all possible values had better be 1. And the individual probability mass function values had to be equal to or greater than 0. Okay, so that's what these two boxed facts are getting at here. Okay, so this is an example that, I'm just going to briefly mention it here, the Pareto family of densities. K could be anything positive, and theta, that's the Greek letter theta right there, could be anything positive. It turns out that this piecewise defined density is in fact a density. I'm not going to do this right here in this video, but I'm going to take a deep dive with the theory of probability people and actually go through these examples right here. So this is not something I'm holding the probability and statistics people responsible for, but just know that that this thing is indeed a density. Okay. Okay, I'm gonna leave that for now. We'll revisit that with the theory of probability people. Let's look at this one though. Okay. Let y be a continuous random variable with probability density function. Given by that, it's a piecewise defined density. Okay. Okay, f of y is equal to 1 over 25 times y if y happens to be between 0 and 5. It's equal to that other thing if y is between 5 and 10, and then it is 0 anywhere else. Okay. So let's actually let's take some time here to look at this. Here we'll kind of expand this and we'll do some computation on the board here. Okay. So f of y, okay, what was it? F of y was equal to 1 over 25y if 0 was equal to or less than y was less than 5. Okay. Hang on, I just want to make sure that's actually true here. Yep. Okay. And let's see, it's equal to 2/5 minus a 25th y. If 5 is equal to or less than y is less than 10 or less than or equal to 10. Okay, and then the other part is just saying it's 0 otherwise. Okay. Okay, so if you're outside of the interval from 0 to 10, this density is equal to 0. Now remember what we said. We said a density had to integrate to 1, and we said that it always needed to be positive or equal to or greater than 0 anywhere. Okay. Clearly that's satisfied by the last thing. Like if it's equal to 0 outside of the interval from 0 to 10, that's fine, right? Equal to or greater than 0 is fine. Now these two things, there's a little bit more of a question, but let's actually sketch this thing, okay? We'll take this a little bit deeper than just this question here. Let's actually sketch the graph of this. Okay, so first of all, it's equal to 0. This density is equal to 0 all the way to here. Okay, then it's equal to 1/25 y if y is between 0 and 5. Okay, so so like at 5, this is a straight line. Okay, 1/25 y is a straight line that goes through the origin and has slope equal to 1/25. Okay, because remember, the equation of a line. Okay, so if I plug in 5 into this, I get a 5th. Okay, so this isn't really going to be to scale, but I'll put a 5th right here, and I'll put 5. I'll put 5 right here. Okay, and this thing, I'm going to put an open circle here because it says for y less than 5. Okay, this is kind of confusing because y is along this axis right here. Okay, so this is y f of y. Okay, so this thing goes like this up to this point. Okay, and then it's equal to 2/5 minus 1/25 y. All right, for y between 5 and 10. Now, if you plug in 10, think about it. So 10 is like right here. If I plug in 10 into this, I get 2/5 minus, right? So watch this. What's f of 10 equal to? Let's just plug this thing in down here, okay? So f of 10 equals 2/5 minus 10 over 25. Yes? Just plugging in what y is right here when I plug in y equal to 10. And what's that equal to? I think, all right, so that's, you know, if I cancel a 5 from the top and the bottom, I get 2/5. So that's 0. So that means this thing is equal to 0 at 10. And of course, it's equal to 0 beyond 10 as well. So what's going on between 5 and 10? Well, really all I have to do, this is also a line. This is also a line. I just really have to plug in 5 to figure out what's going on. But f of 5, okay, f of 5, what's f of 5 equal to? Well, I use this equation right here. It's going to be 2/5 minus 5 over 25, which is 2/5 minus 1/5, which is 1/5. Okay, 1/5, which is, you know, the same as this function was here. So actually, this thing meets it perfectly right there. It goes down like this. Okay, so that is the graph. This is the graph of f of y. Okay, that's the graph of f of y. Why does this thing add up to, why is the area under this curve 1? Okay, well, we just need to think about, okay, if I were to integrate this thing, that means I would be having the area under this curve. Okay, so the integral from negative infinity to infinity of f of y dy is equal to, well, look, I'm gonna get nothing outside of 0 to 10. And then all the area is going to be gotten at here. And that's just the area of a triangle, isn't it? So that's going to be 1/2 times the base length. The base length here is 10 times the height, which is 1/5. Yes? Okay. 1/2 times 10 times 1/5. Okay. Well, 10 times 1/5 is 2. So I get 1. Overall, which is good, because that's what definitely should be true about that. Yeah. Okay. So what about this other probability? The probability that's on the screen right here, the probability that 3 is equal to or less than y is equal to or less than 8. Let's look at that. Probability that 3 is equal to or less than y is equal to or less than 8. Well, where in the world is 3 and where is 8? So let me see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So here's 3 and here's 8. So that means I want this. Yes? I want this area right here between 3 and 8. Yes? Hopefully you can see that decently well. Okay? I want that area between 3 and 8. I know that the entire area is 1. We just did that. The entire area under this triangle is 1. So really what I can do is I can kind of like compute 1. I could take 1 and then I could get rid of these little triangles on the end. Yeah? And get rid of those little triangles on the end. I could, of course, just compute the integral from 3 to 8 of this function, but then I would have to break it up right here in the middle at 5 because the function changes there. Okay, and that would be a little bit annoying, but sort of an easy geometric way to do this is just to go 1 minus, okay, the area of this triangle right here. Okay, let me just call this A1, and let me call this area right here. Let me call this area right here A2. Okay, so this is A1. This guy right here is A1. And that guy over there is A2. So this is going to be 1 minus A1 minus A2. Okay, and how do I compute A1? Well, it's going to be 1 minus, okay, this is a triangle, so it's going to be 1/2 times the base length of this, that's 3, times the height. Well, to get the height of this, I need to plug 3 into the density. Okay, I need to plug 3 into the density. And which definition do I use? Well, if y is 3, I use the top one. Yeah? So it's times, let's say f of 3. We'll just write f of 3 here temporarily. Okay? F of 3 here temporarily. And then it's going to be minus 1/2 times, okay, what is the base of this triangle over here? Well, it's 2 times the height of this triangle, which is f of 8. Okay? And let's see here. What is f of 3? So let's just compute this. This is 1 minus, like 1/2 times 3. That's 3/2 times f of 3. F of 3, again, I just used this top definition, so that's times 3/25. I'll write this down here. Minus 1/2 times 2 is just 1. Okay? 1/2 times 2 is just 1, so it's minus f of 8. Well, for 8, I have to use this second definition for the density. Okay? I have to use the second definition for the densities, because 8 is between 5 and 10. So I have to plug it into this second definition right here. Okay, so it's going to be, right, 1/2 times 2 down here. 1/2 times 2 is 1. F of 8 is 2/5 minus 8/25. Okay? Whatever that ends up being, okay? Whatever that ends up being numerically, okay? But we have the numbers now, okay? Let me just kind of quickly do this, just because it would be a good idea to do it. Okay, let me just do this. All right, so this is going to be 1 minus 9/50 minus, oh boy, okay. So to find a common denominator here, it would have to be, I have to multiply by 5 over 5. This would be 10 minus 8, which is 2 over 25, okay? Okay, because this would have been 10 minus 8 over 25. Okay, and then what do we have here? So it's going to be 50 minus 9 minus, multiply this by 2, minus 4 over 25, or over 50, sorry. Okay, 50 minus 9 minus 4 is 30. So 9 plus 4 is, 13. So it's 13, so it's 37 over 50. That's what the probability is. Okay? All right, so that's kind of an important example. And by the way, this example is going to come up again and again later on. Well, at least one other time later on. So I think I'm going to pause right there, and you can kind of rewind, think about this a little bit. But that's how you compute that probability. All right. And again, you could have used an integral. You could have used an integral. You could have integrated from 3 to 8 and pulled it off that way. But I don't know. It's kind of nice to use geometry too, if it's at all possible. And we were able to do that here. All right. So I'm going to stop this video right here at this point.